All right, welcome everybody. Thanks for coming over to Minneapolis campus here today for our Frontiers in the Environment talk. And I think there might be some other people watching online, so welcome to those of you who are watching online today. It's my pleasure to introduce our speaker for the day, Doug Tiffany. A little bit about Doug. He has over 20 years of experience as a production economist and has multiple degrees in agricultural economics. His research and work has kind of run the spectrum of biofuels and bioproducts, work on ethanol, biodiesel, even doing some look at cellulosic fuels and also converting poplar trees to energy. Beyond that, he's even worked on issues such as avian flu. So he has a really wide background in terms of the research and work he's been doing over the years. He has a couple of online projects that are pretty cool. You might want to check those out too, through Extension and elsewhere, answering questions such as, should you buy an alternative car? And should you subscribe to community solar? And so really someone who's digging into a lot of these issues that are present and that we're talking a lot about nowadays. His talk title today is Replacing Agricultural's Most Energy-Intensive Input Using Wind, Water, and Intellect. I should also mention that Doug is a research fellow with the Institute on the Environment and also with the Bioproducts and Biosystems Engineering Department in CFAN. So please join me in welcoming Doug.
Thank you very much, Todd. And welcome to the audience here and those who might be out watching on the internet. Well, I want to tell you this has been just a wonderful project for me to be involved with over the last couple of years, and it's an important topic. And you say, well, what's so exciting about ammonia? We've been making it for 100 years, but right now we realize there's other ways we could make it, and it is very important. Probably some estimate that 50% of the nitrogen in our bodies is a consequence of nitrogen that was fixed from the atmosphere by the Haber-Bosch process. So it's right with us all the time. So I'll move along and introduce a bit of our team. We have we have the panel of four gentlemen on the left. Those are Ed Kussler, Alan McCormick, Padromas Dietides, and Paul Dowhauer. And they are doing great things in chemical engineering and material sciences. On the other side, we have Mike Reese, who works out at the West Central Research and Outreach Center at Morris. And he really got this project going by trying to get funding to put up wind turbines out at that research station and do research to see if we could make ammonia out there in that area. We have Roger Ruin, who's kind of working on something that's related, which is non-thermal plasma, another way that ammonia could be made. We have Ken Valentis, who is working on biochar and ways to handle nutrients that way. And then I'm there, and we have Stephen Kelly, who's really looking at the policy side of things from the Humphrey Institute and how there may be different incentive structures that might be very valuable. It's been a great team to work with, and I can report today we've had some interesting progress, and but I want to talk about where this project come from. And it came from this idea that we do have some excellent wind resources in the upper Midwest, and you can see those areas that are in purple, and we have some of it in western Minnesota, and that's where Morris is. And sometimes we might have great wind resources, but we don't always have the opportunity to transmit and sell that power if we have inadequate transmission. So sometimes you might see an idled wind turbine, and that's been curtailed because there isn't room to take that power away. So when that happens, you say, what's the problem here? We could have this investment. Maybe we should look at it a different way. Maybe we should think about trying to use that power locally to make something we need. And that's where the thinking went to, can we produce something that farmers in rural Minnesota need? And one thing they do need is ammonia. It's one of the most important inputs in raising many of our crops, and it's a compound with other fertilizer products like phosphorus. So this area that shows the Corn Belt looks like a demand area for ammonia, and some of these are areas well endowed with wind. So anyway, so we have local motivations, stranded wind energy, and we have the opportunity to do distributed production, and that would be a smaller scale, but closer to the ultimate users. And Some years ago, the farmers were quite concerned about the volatility they were seeing in the price of ammonia that they were paying for. It got up to $1,000 for a short time in 2008, and went up and down. And they saw this volatility partly because it was related to the price of natural gas. Well, farmers sometimes want to invest in opportunities for their businesses, and they said maybe we should be involved in making this ourselves or owning this production capacity. So anyway, that's part of the motivation. So plans went ahead, funds were raised to put up wind turbines at University of Minnesota Morris, and here you see an aerial view of the research station, not the campus where the undergrads are. This area is along the Pomme de Terre River, which is at the edge of this photo. The campus is about a mile away in the city. One of these turbines is exclusively for the campus, and this was the one that's involved in making ammonia today. Here's some of the buildings involved in the ammonia production.
How far does the West Rock land go?
How far is it? Oh, well, I really can't tell you all the, but you can see a fair number of the fields here. I think there's some more that extend further this way. So anyway, anyway, to make ammonia, it's NH3, right? Pretty easy to keep track of those two important chemicals. And it requires hydrogen. And here it shows a picture in 1928 where some Norwegians who had lots of hydropower, and they still do, and at that time they were the biggest fertilizer producers in the world because they had the power. And they were getting hydrogen by performing electrolysis on water. At Morris, the process is like this submarine, and they have a hydrolyzer made by the same company that makes it for our submarine fleet. But we do just the opposite. Instead, whereas the submarine uses seawater and produces oxygen to keep the crew alive, they vent off the hydrogen. We do just the opposite. We're going to vent off that oxygen and keep the hydrogen, and it'd be very pure hydrogen that could be made into ammonia. So that's how we get it from water. So. This is a picture of the other thing we need. We need to get nitrogen. And there's two ways to do it. One would be a membrane technology, which is pictured here, where compressed air is pushed through and it gets separated. Other way is with pressure swing adsorption, and that is the process that's being used out at Morris. And it's a machine that's made for commercial use in a number of places. So the next thing I'll show you here is the ammonia synthesis machine. And this is to do the Haber-Bosch process, which requires high temperatures and high pressures for both streams of hydrogen and nitrogen. These two streams of gases are pushed over a bed of catalysts, typically iron filings. And there's been all kinds of research to find just the right mixture to make this work most efficiently. So that's a big part of it, and this was a machine that was built especially for the experiment station. Okay, we were able to really get this thing running well in 2014, and the first thing they tried to do was solve all the problems, make sure it worked just the way it was supposed to, and then they really developed a safety manual, how to do this carefully. And this may be helpful for smaller businesses that might try to do this themselves. So that's one of the research outcomes. But one thing that was learned is that the molar ratio is very important. So that's the relationship of hydrogen molecules to nitrogen. And they tried different ratios like 3.0 and 3.2, and they found that 3.5, so the overload on hydrogen works better in this system. So, and it required less energy to do the process. So those were important lessons learned. Also, they learned how to run this plant continuously. And this is a big lesson because, come on, if we're going to talk about something that might be commercialized, is this really going to work reliably over hours and hours of operation? And this was a way to learn about maintenance and other control challenges. And the instrumentation was improved in this process. So then, after we had some operational history, it was time for me to do some other work. And that's when I started to look at what the costs of this ammonia that would be produced at Morris would be. And because the operation at Morris is very small, it would produce 28 tons of ammonia per year. And most of the plants in the country would produce 100,000 tons per year. So there was a necessity to scale up this. And when things get scaled up, the costs of capital are lower per unit of capacity. And so this is what I did. I applied some mathematics to the situation and modeled the details of the plant we had at Morris as if it was a big plant, fully up to scale with many of the others in the industry. And so what I learned is the overall cost would be $941 per ton. Now, currently, farmers are taking delivery in southern Minnesota for things like $524. So it's a bit more, but what was interesting was to break this down. And here's where the cost came for doing the hydrogen. Here's where the nitrogen, the cost of getting the nitrogen, and then here's putting it together, the synthesis of ammonia. So that kind of breakdown was helpful and shared with the chemical engineering staff. One thing that stands out to me as an economist is that this is a very capital and energy intensive type of production. And if you look along the bottom, depreciation on a 20-year basis is a very large cost. And then there's the interest on 40% of that capital could be there, 17%. And then the electricity purchased is the next big item. So that's the kind of industry this is. Not a lot of labor involved, not other disposables. Set this thing up and keep it running is typically the way you go with something that's so capital intensive. Try to make it run around the clock. I broke this down in some more detail, and here's some graphs to show it. Up in the far right is where I look at the capital costs and the associated interest. And the biggest portion has to do with the ammonia synthesis, followed by the hydrogen production. And then there's the nitrogen production, which is more minor. But when we get to where does the energy come into this, hydrogen takes the big portion of cost. And you can see that the amount is pretty small for nitrogen. And then the ammonia synthesis is there for that amount of energy. So when I put these things together, this is the sort of breakdown. But it's important to understand these when we slice them apart. And that's why I did it that way, to guide our research efforts a bit and validate that. So when we're talking about having distributed production, we're talking about producing ammonia close to the users, closer into farm country. So then it begs the question, how does the ammonia get to the Minnesota farmers? Well, what you see is a map of the pipeline system, and typically the ammonia that comes to Minnesota would come from Oklahoma and some of the natural gas fields there. And it's cheap, and they want to make it into something close to where it comes out of the ground. And it can be pushed around in pipelines just fine. And what I did then was to say, well, what are the costs of production in these different places, and transportation and greenhouse gases? Let's try to segregate these differences between doing it in Morris or Oklahoma. This table helps with that. To push that ton of natural gas from Oklahoma to Minnesota costs $40. That would be the typical tariff. And then to do trucking from Mankato to Morris would cost $22. So there's a transportation differential versus if you just did it right there at Morris. And then we look at where the environmental story to produce that from natural gas emits 3,700 pounds of CO2 equivalent. And then there's electricity that's used to do it. And then there's pipeline energy and diesel. So here, this would be the embedded CO2 to produce and then send that product up to Minnesota. So there's our 62, and just for interesting figuring, if we had carbon taxes of $28 per ton, it would be the same amount. So a lot of discussion was made about thinking about carbon taxes about 30. So anyway, I wanted to put that before you. But if we did it at Morris, these costs would be eliminated, and this amount of CO2 emissions would be eliminated by having more distributed production. Okay, carbon taxes, I brought that up. Here's a graph I made showing different rates that might be out there. And again, I calculated that there would be 2.18 additional tons of CO2 emitted by something in Oklahoma and transported to Minnesota than something produced right in Minnesota. So I looked at that and what that might be with different rates. We'll see what happens. This is in the policy field, and we'll see what happens in that. Well, next, I'd like to tell you a little bit more about chemical engineering, and I want to say I learned a lot more chemistry on this project than before, but I was always interested. So this is, first of all, a typical reactor, and nitrogen and hydrogen come in, they're compressed, they are under some high pressure here, 150 to 300 atmospheres. They go through, they get to a reactor, so they're already under pressure, they get hotter, there's the catalyst there, and probably 15 to 20% would be made into ammonia. Some of the other gases would just be nitrogen and hydrogen. They condense out the ammonia, and that would be the product. Some of these other nitrogen and hydrogen get pushed and go around again. They get reheated and pressurized in the process. Now, the concept that chemical engineering worked out would be to take these same gases, run them through this compressor, and guess what? We're down to 20 atmospheres of pressure. And then it goes to the reactor, and then there's this absorber, which helps in this process. It makes the catalyst more efficient, essentially. So this was the novelty that they did, and I'll explain that in a little more detail. And so there's different ways to try to make a really viable small unit to make ammonia. And here are the concepts: better conversion on the first pass over the catalyst, a better absorbent, or operating at lower pressures. And so the opportunity is to look at different substances, and one that has been used by others is magnesium chloride, a very common compound. And what we know is that 100 grams of this, probably about like the amount you would hold in your hand, like a piece of soap, could hold 100 liters of ammonia as a gas. Now, how did all that get pushed in there? Well, what's very interesting is that magnesium chloride is a crystal, and that ammonia is liquid-like when it's held inside that crystal. So that absorbent sucks that right in and holds it. Now, there was a lot of work done by the group in chemical engineering looking at absorbents. And here they looked at magnesium chloride alone, and then they added some alumina. And what they found in the first case was there was some variability in how well this performed. And what they learned later is by adding another metal to this, they were able to get some reliability. And that's very critical when you're trying to industrialize a process. So that's a major finding. And by the way, the first author on this was a young man who got his bachelor's degree here. So brought in some good training for some young people and other grad students. So here's another important outcome of this whole thing of using absorbents. And this particular graph shows what we would have if we just ran this without an absorbent. And this is the amount of nitrogen that gets converted to ammonia here over a certain amount of time. And it kind of gets up to this point, and it kind of stays there. And that's describing this 15 to 20% conversion on a single pass. But what we see here is when there's some magnesium chloride nearby, that helps the process and allows for greater conversion by whisking the formed ammonia away from the surface of the catalyst. I mean, that's how I talk about it. Probably someone would need an electron microscope to tell me if it's really true, but that seems to be sort of how it may operate. So that's been some very interesting work that's come out of this, and allowed for some very high rates of conversion in one pass, approaching 90%. Wonderful. Okay, so even more work. Another outcome of this work with absorbents, and I touched on it before, is to think about the operating pressures. And the first two lines, the black one and the red one up above, show what happens to the reaction. The first one is at 55 bar of pressure. The red one is at 90 bar of pressure. These are pretty similar. But if you can go at 55 bar if you are able to do separation with the help of this absorbent. So by making things get to lower pressure, this is a great opportunity to make something at smaller scale that could be produced. So how do I, as an economist, look this whole thing over? Well, I told you before that this plant at Morris, if it was a large scale, would produce the product for $941 a ton. Not so bad, not so far out of range. Farmers have paid as much as that in recent years. Today the price is $500, but a few years ago it was $700 per ton. But if we apply some capital cost reductions due to reducing the amount of recycle and perhaps the energy involved, that would reduce the cost by this amount, 246. That's just an estimate, but that kind of helps us determine our direction. Then there's the transportation that would be eliminated, and then if there were avoided carbon taxes. So if there was some benefit for that, for this type of production, it gets the local production cost to $568. This is the value that I see of this absorbent and the opportunity to run things in a distributed fashion. So we can talk about that later. But let me just summarize. This has been a very interesting project. It's moving along, but it's by no means finished. The pilot plant continues to run to validate and improve, and there's much more work going on with the absorbent technology. It's been patented, and some overtures have been made to businesses that may choose to commercialize this. And there's, of course, interest going on with these other technologies with biochar and non-thermal plasma in the fertilizer area. And then we need to think about research incentives, and Steve Kelly at the Humphrey Institute is working on that, and I'm working with him on that. And then there's some work on using ammonia as a fuel. And ammonia is a pretty good fuel. It doesn't have the density of diesel, but NH3 can be combusted in an engine. And so there are opportunities where a remote plant out in the desert, up in the Arctic, could make ammonia, and maybe somebody just needs to use an engine for certain times of the year. And this is what this research is looking at, how it would work in those engines. We're interested in the small scale ammonia. Think about places in this world that do not have pipelines available full of natural gas to make ammonia and other fertilizers. And think about places that don't have roads, but probably have some productive soils that could make use of locally provided nutrients. So these things are open questions, and there's probably more, but I just wanted to give you a sampling of where we are on this project. And I also want to thank you for attending, and I want to thank our sponsors that have helped us with our funding. And we've worked with a number of different granting agencies, and it's been a very favorable relationship for the university and for our project. So thank you very much. I'll be happy to entertain questions from this group, or Todd will handle that.
One question about cost of production.
Let's see. Gosh, so many. I guess the first question is, your last cost estimate is now down about around where farmers are paying now. Is there an opportunity cost for being able to do it locally and on the farm? That is, could the fact that you had control over the process yourself, could that make up some cost difference as well?
Well, I think that's, I was thinking on the farm is one possibility, but I was thinking there's certain maintenance issues and engineering issues.
Or maybe
I
as
think
a
that ultimately
local co-op.
could be a local co-op, might be a better fit. But scaling things down to, say, a county level or something that could work with a few wind turbines that sometimes get idled and use some of that power to make something locally is what got people going on this idea. We have heard from some Canadians who are in an area that say, well, we've got quite a bit of extra hydropower, and maybe we should make some with that. We have a lot of water at certain times. There's other people thinking about, can we do this with solar? In some parts of the country that you don't think of have a lot of solar, like the Arctic even. They think about in the summer, could we make a bunch of ammonia and use that fuel in the winter? So sometimes when you start a project, you get some new questions, and they're good.
Just an extra comment on that, Doug and Prodramus Diotidis are also looking at the question of the energy cost. If you are using stranded energy, is it fair to charge that at commercial rates, or can you have free or even negative cost energy?
That should be something, yeah. Yeah. About the cost of production and the economy of scale, you talk about the pilot plant versus the commercial size estimation. What is that range? Is doubles, triples?
Okay.
That's one thing. And that 36% of cost of energy relates to that in a way that if you increase that, will be reduced. You reduce that, and will be increased. Well, besides that, there are two cost items that I didn't see that mentioned, at least. The oxygen production, which is very pure, it's a specialty chemical, can be used in a different scale of production. It may be something that can be reducing cost. And the other part is the regeneration of the adsorbent. Was that taken into account in your cost?
Okay, great questions, and Alan may want to answer part of that, but let's go to the absorbent first. It's my understanding that a change in pressure allows that absorbent to release the ammonia it has held. So it might require something that would work in series with different amounts that would rotate around and accept and then release the ammonia in that fashion. The other question you had was about scaling. And I was scaling things up between 10,000 times the size of Morris or 100,000 times. So there's some very big plants out there. So that's what I did, and it was more of a mathematical approach, but these costs go down when you build something bigger. And there's probably more work I could do or other assumptions I could apply. But I think it puts us in the ballpark, and this same methodology is used in lots of different chemical plants.
And about the regeneration, our best guess at the moment is if we do it right, it won't cost a lot. But there's still some more work to do to make sure we know how to do it right.
Yeah. Or maybe just capital initial.
I have a quick question for you. So I'm curious what's causing the price variability in the more commercial ammonia. What pushed it up to 1,000 and now it's dropped it down to 500?
I looked at some figures a couple nights ago about the prices of ammonia. And there was a time in the 60s where it did change a bit. I think we had a certain amount of natural gas coming online, and here was the price. And there was a certain amount of infrastructure that could move it. And so it was kind of a fit. When we have expansion in corn production, people want more ammonia or some other nutrients that are bonded with ammonia. And that can push it. One would say, well, did the price of natural gas really change enough to change the price of ammonia? And the more recent time of, say, 2013, 14, 15, it seemed like these got unhitched. And the price of ammonia went far more than we would have expected. So maybe that was partly due to the capacity of the infrastructure to get it moved. But anyway, economists look for those things and say, well, if we got some sort of market failure we don't quite understand here. So anyway, good question.
I've got another one for you, but I think, Lewis, do you want to ask a?
Yeah, another one. Okay. I have a whole list. So one of the, well, which one to ask? In Germany, they're thinking about the hydrogen as a fuel. And here we've been fixing it more with nitrogen to make ammonia. Are there other uses for the hydrogen? That is, and related to that, I guess, is are the infrastructures for moving ammonia around, are they dedicated to ammonia, and are they mixed use kinds of
Great.
infrastructures?
Ammonia, we have quite an established infrastructure in this country to move it around, and trucks and delivery and pipelines that can do it. And we have a fairly good safety record with it. So other parts of the world look at us and say, how's this working? And it's working pretty well so far, I'd say. But, and it can be useful as a fuel. It burns very cleanly. You think about it, you got the N and the H of the ammonia, and you end up with N2 and water vapor. And that's pretty clean from the emission standpoint. It doesn't have near the density as diesel fuel or others, but it will work. And sometimes it even works better with just a small amount of diesel in a mixture in an engine. So yeah, Will Northrup of Mechanical Engineering has some work that he's doing now with engines run with ammonia. You asked about hydrogen, and could we do something with that? And we could. And in fact, there is a small tractor out at the West Central Research and Outreach Center that could be run with hydrogen. One thing that I've learned is that the tanks are more expensive for such a vehicle, and you can't get a lot of fuel in the tank at one time. Some early machines were made for aircraft and Air Force bases that ran on hydrogen. It's an expensive tank on a small vehicle that could tow something around. And actually, it would be possible to hold more ammonia if it was in the form of, more hydrogen if it was in the form of ammonia. Having it in that molecule is more efficient packaging.
So are those fuel cells that run on fuel cells, or are they combust?
Either one.
On Doug's point about hydrogen storage in ammonia, there's a lot of research at various places, but especially in Japan, with looking into the model of generating hydrogen, making ammonia, moving the ammonia because it's so easily transported, and then regenerating the hydrogen where you need it.
What about the use of oxygen, the pure oxygen? Have you been thinking of that?
Well, at this point, we haven't done that at Morris. But let me say, that's a great question. And if we were to take that ammonia that has already been produced, we could use some of this oxygen to make it into urea. And that would be ideal. And look at here, across our countryside, we have a lot of ethanol plants, and they produce some good oxygen. And some clean CO2. So, I mean, that's our opportunity to make urea. I misspoke of CO2. So oxygen has its opportunities, but at this point it's too small to worry about. In a submarine, that's what they want.
Or in the larger scale that you're thinking about,
Yeah.
1,000.
Yeah. So, other things that people can do with hydrogen is some of the power plants use hydrogen and they put it around the windings for the generators. And that can keep those windings much cooler and be more efficient. So you think, oh, this would really be dangerous. But it's done quite often in power plant situations, hydrogen, used that way.
I have a less technical question for you, if you don't mind me throwing this in there. So pre-Institute on the Environment, back in the days of IRI, I remember seeing these early proposals for the work that you guys have been doing now, probably for about a decade, I want to say. It's been a while.
Not quite that long.
Not quite a decade, but it's been a while.
But
Can you just talk briefly about the importance, though, of long-term research and kind of sticking with a project and following it through? Because where you started is I'm guessing, a bit different from where you guys ended up now and where the point you're at right now.
Well, that's a great one. It seemed like, oh, this would be neat. Let's hurry up and build something. And I thought it would happen a little faster than it has. But this opportunity to use absorbents is, I think, a very important step. And we should reflect back on when they started making ammonia with Haber-Bosch. Lots and lots of research took place on determining the very best catalysts. And there's some companies that have all kinds of trade secrets in this area too. This Halder Topsoe company of Denmark knows all about these wonderful secrets of the right mixtures. So anyway, these things take time, and it's worth going. Sure, we had lots of ammonia. It's available. We have all we want. But guess what? We can make this, and we can make other things different ways. And we should always be thinking about the fate of the chemicals we make and how they end up in the environment, and also our greenhouse gas emissions in making these and moving them around. So that's always to be considered.
Just one more comment about Doug's vision and Mike Reese's vision, and the early investors in getting the pilot plant started up, the wind to ammonia plant, using conventional separations and catalysis in Morris. When we present on this work at the Ammonia Fuel Conference, there is excitement there about there being a real operating benchmark. Nobody expects that it is necessarily going to be the most economically viable as a first attempt, but it is a benchmark that's worth study. And one of the most important papers that resulted from that was analysis of steady state runs at that scale that simply had not been done before.
So Doug, I want to give you the final word then. You mentioned this briefly just a moment ago on kind of where the project's heading, but what are you excited about next in terms of where the project is going and what might be on the horizon for the research team?
Well, there'll be more work, and guess what? They'll need to build some of these absorbent chambers. And I dearly would love to see some of these built, whether they're built on campus or we have to find a contractor, because from that we could say, all right, if we had to build something bigger, then we could scale it up, mathematically to get an idea. And that would be very useful, very useful. So there's a lot of good work to be done, and ways to think about our nutrients that are applied to the land and used to grow so many of our crops. This is a wonderful topic, and if you have more interest, I'll just share with you, there's a couple of wonderful books on the topic that are out there about the Haber-Bosch process. This Alchemy of the Air is more on the personal side. Enriching the Earth is by Smeal, who's up at Winnipeg, and this is a very thoughtful book. This one came out first. This one has more of the personal side of these two men, Haber and Bosch, who both won Nobel Prizes. So that's something that you or the audience might be interested in. These are both excellent reads. And they also talk about they were really fearful that Malthus was right, that there was going to be mass starvation across the world until this breakthrough occurred, and it occurred under the pressure of World War I. And in fact, the Haber-Bosch process probably extended World War I by 2 years because the Germans didn't run out of ammunition as fast. So anyway, some good and some bad. Now here's the two men, Haber and Bosch, and here is the first reactor, one of the first reactors they had to make ammonia, and they used a gun barrel that could withstand the pressure. And these are the fathers of high pressure chemistry. Haber did the work in the lab and theory, and he was scolded by some of the ranking chemists at the time. And then Bosch was a guy who knew how to build this stuff. And he was from a family of plumbers, and he really knew how to put things together. And he industrialized the process. So they both won a Nobel Prize at different times. So it's a great story about the march of science and how sometimes things that happen on the military end affect us all in our daily lives in terms of R&D. Thank you very much.
Please join me in thanking Doug for today's talk. Just a quick reminder, we'll be back on the St. Paul campus on April 5th for our next session. So thank you, everyone.